Let us consider the case where single phase half wave rectifiers are connected to RLE load. It's a different kind of load which represents a DC motor as discussed earlier. If you just consider one diode in series with the load and source, we can say that D1 is on when the input voltage Vs is greater than the EMF E. Or if you assume D1 is equal to off, D1 is off, voltage across VD1 will be Vs minus E. Why? Because there is no current flowing in the circuit, so the voltage across inductor resistor will be 0. So the voltage across the diode will be Vs minus E as evident from the KVL. So D1 will be on only when Vs becomes more than E, and let us say that it happens at delta, at the delta angle shown here, and that delta is equal to sine inverse E by Vm when the voltage Vs becomes equal to E. And when does D1 turn off? D1 turns off when the current through the diode becomes 0. Why? Because once it turns on, the current follows the solution of this differential equation. Vs minus E is equal to Ris plus L dis by dt. So if we solve this differential equation for the instant at which the current becomes 0, we will get the angle beta, and the diode turns off at omega t is equal to pi plus beta, where the current becomes 0 as seen in earlier case. And how do we calculate the average output voltage? The average output voltage VO average is equal to VO dash average, and it can be calculated by integration as discussed earlier, and this is the expression for VO average which depends upon beta and delta. We can also see that the volt seconds are balanced across inductor. So this a particular area A1 is equal to the area A2 in periodic steady state. And what is the current flowing through the source or diode or load? It's the same because it's a series circuit. So the waveform is similar to the case of RL load, but the average value of the current waveform, like the average value of this green color waveform shown here, is which is denoted by IO average, is VO average minus E by R. And the interesting thing about the voltage across the diode is that the diode has to block minus Vm plus E. It's more than the peak of input voltage in this case. Why? That the voltage across the diode is Vs minus E, and when Vs is minus Vm, obviously this EMF E adds up to the voltage, and now the diode has to block more voltage than the peak value of input voltage. Please note that this is the repetitive reverse maximum voltage that appears across the diode, which is denoted by VRRM, and it's a popular specification of the diode. Now consider the case of freewheeling diode. So we have two diodes. One of them is known as freewheeling diode, and the load is again RLE. As discussed earlier, if we apply KCL at this particular node, ID1 plus ID2 is equal to IL. So IL cannot be negative, it can only be positive or 0. So when IL is always positive, that mode of operation is known as continuous conduction mode, CCM. And when IL is positive or 0, that mode of operation is known as discontinuous conduction mode. So in discontinuous conduction mode, there are three states that appear. D1 on, D2 off is one state, which is in the positive half cycle of the input voltage, and in the negative half cycle we can have two states, D1 off, D2 on, or both off. When will both be off? When the current goes to 0. The current goes to 0 faster course, the current has the exponential fall here in this interval, but the exponential fall will be faster because now it is aided by this E. So there are three kinds of segments in voltages VO dash and VO. VO dash is equal to the input voltage in the positive half, again after the input voltage has crossed E. So it has a sinusoidal segment. And then when D2 is on, VO dash is 0, and that happens for an angle beta after pi. So that is this particular segment. And the third segment is when VO dash is equal to E. VO dash is equal to E when none of the diodes are conducting. Similarly, the output voltage waveform VO will also have three kinds of segments. It can be explained from the current waveform as well because it is proportional to the current IO or IL, inductor current. So the inductor current will have three segments. One is the sinusoidal plus exponential segment, and the second segment is exponential segment, exponential fall segment, and then the third segment is just being 0. So there are three segments of inductor current waveform, and consequently there will also be three segments of output voltage waveform. So this segment and the second segment and third segment. Output voltage is equal to E in the third segment. In the continuous conduction mode, the state of both diodes being off will not be there because IL has to flow always. So either D1 or D2 should be conducting. That is what is seen in the second figure here. In the first half 0 to pi, D1 on, D2 off, and in the second half D1 off, D2 on, just similar to the case of an RL load, because once the current is continuous, it doesn't make any difference to the source side and source and two diodes. As long as the inductor current is positive, if the source voltage is greater than 0, D1 will conduct, D2 will be off. If it is less than 0, D2 will conduct and D1 will be off. That is seen in the second set of waveforms shown on the right side in the continuous conduction mode. The average output voltage will obviously be different in continuous conduction mode and discontinuous conduction mode. In the discontinuous conduction mode, the average voltage is a function of delta and beta as shown by this expression. It can be found by integration. And in the continuous conduction mode, average output voltage is just Vm by pi because it is similar to the other case. Again, the average output current is VO average minus E by R in both the cases as shown here. Let us try to summarize what we have learned so far. We have looked at 6 kinds of 1-pulse diode rectifier circuits, and let us look at the circuits and the most important waveforms that we are interested in. So the first circuit that we have considered is a single phase half wave rectifier. It's a rectifier which has only one diode and the load is resistive. We are interested in the output voltage and input current waveforms, which are shown in red color and green color respectively next to each circuit. So in the first circuit, the output voltage is as shown. It is either sinusoidal variation or 0, and the source current will also be similar to that. And when we have an L filter and R load, the output voltage will have sinusoidal plus exponential kind of variation for some interval, and then output voltage will be 0 for some interval. The source current will also have a similar waveform in that case. What do we observe? We observe that one segment of input voltage is appearing at the output directly or in a kind of distorted form. So in the first case, the input voltage, the positive half cycle of input voltage is directly appearing across the output and the negative half is not appearing. So one segment is appearing at the output. And in the second case, one segment is appearing at the output but in a modified form. That is why these rectifiers are also known as 1 pulse rectifiers, and since diodes are used, we are calling them as 1 pulse diode rectifiers here. There is another thing that is very special about these 1 pulse diode rectifiers. What is the source current? How does it look like? It looks like a DC waveform as per the notion of DC and AC that we have defined at the beginning. It has AC component, it has harmonics, it can have fundamental and harmonics, but it also contains a finite average value or DC value. That is true. These both characteristics are true for all the other circuits that we have considered. So the output voltage is again having 1 pulse of input voltage in these cases also, and the source current has a DC component, and same is true even in the case of RLE load. And if the source is such that it cannot accept DC current to be drawn from it, there will be a problem. For example, if the source is a transformer, we have a step down transformer, and then after that we have connected this rectifier, we have to make sure that the transformer does not saturate even when this additional DC component of current is flowing. That is the problem with 1 pulse diode rectifiers, and that is why they are not very popularly used. However, they are a very good starting point to understand many other rectifier circuits, and that is why we have discussed them here in detail.